This is a LLM seminar, so we're hybrid broadcasting through Zoom.
Oh, you might just need to click on the slide.
Sure, there should be one. Sreejith is a speaker. So he did his PhD at Penn State in the United States and postdoctoral fellowships in Northeastern in Stockholm and Max Planck University, and is now at IIESR Pune, and is currently visiting Oxford and visiting us for a couple of days. And he's going to talk about quantum Monte Carlo of quantum developments.
Thanks, Stephen. Thanks for introducing me, and thanks for giving the opportunity to give the explain this work here. Yeah, okay. So this was work done a couple of years ago with Fabianelli, and most of the hard work in the numerics and in processing the data were done by Bhupen with the Fabian student. Okay, I'll give a very broad introduction to diamond model, just so that everybody's on the same page. Diamond model is a good example of a strongly constrained, locally constrained model. The model can be quantum or classical. So let me first describe the configuration space of the diamond model in the classical system. It essentially consists of a graph. In the work that I described here, I'll consider a square lattice. Diamonds are degrees of freedom that live on the edges, such that there's a constraint that exactly one touch every vertex. It was originally introduced in the context of some in describing some effective to make an effective description of some physics in chemical systems. But since then it has been studied in various other contexts, particularly in the math combinatorical probabilistic combinatorics community in the form of domino tiling problem. It has been used to describe the effective physics of spin liquids. It has been used to study, used as a model to describe critical phenomena that occur in spin systems. It has been used to describe locally constrained, to model other local constraints. It has been used to describe the constraints that can be imposed using Rydberg atom interactions, and in certain special cases, it can also be used to model or to construct effective description of certain localization phenomena. Okay. Now we'll go to the more specific context of 2D dimer model. If you have a classical dimer, an ensemble of classical dimers with no interactions, by no interactions, I mean that the ensemble of dimer configurations is described by the set of all possible allowed configurations where the constraints are satisfied and these configurations are allowed with equal probability. That describes the non-interacting dimer model. This can be mapped, correlation functions in this can be mapped to correlation functions of fermionic system, and this has been known since 1960s. If you consider an interacting dimer model where we weight the probabilities of describe the probabilities of the dimer configurations using an interaction between dimers. And the simplest interaction that has been studied is the interaction where there is a attractive, or where there is an effective cost, or cost when there are two parallel dimers in a plaquette. If you consider a partition function that is defined by this interaction, then we can construct an interacting dimer model. The interacting dimer model is not exactly solvable, at least not in the same sense as the non-interacting dimer model, which could be mapped to free fermions. The interacting dimer model can be mapped to a height model, a sinusoidal model, with the action of this one, where G is the Coulomb gas constant, which describes the fluctuations of the height, and this describes the tendency of the tendency of the interactions between the dimer to cause the dimers to align in certain directions. In the case of non-interacting dimers, which can be mapped to free fermions, you can calculate the effective partition function, and you can show that G with this notation is exactly equal to half from the exact solutions that you can get. Yeah, and for the interacting dimer model, the Coulomb gas constants can be estimated by calculating the correlation functions between dimers and comparing numerically calculating the correlations between dimers and comparing those correlations with the correlations that you can get from that can be predicted from the height model. The height can be related to the dimers as a vertex exponential of the height function plus a gradient term, and using that you can calculate the dimer-dimer correlation function, and you can compare that dimer-dimer correlation function to the correlation function that you can get numerically using Monte Carlo. From there you can get an effective value for G as a function of the interaction strength between the dimers, and using this you can map out the G as a function of the effective interaction strength V by T. And this was studied by Fabian in 2006 at infinite temperatures, where the interaction is effectively zero. G turns out to be half, as shown in this plot, and at low temperatures, the G increases. In other words, when the attractive interaction between dimers on the same plaquette is higher, G is larger. When G reaches 4, there is a KT transition to a columnar 4-4 symmetry broken columnar ordered space. Okay. Now we go to the quantum version of the dimer model, where the Hilbert space is formed by the orthonormal basis made up of the classical dimer configurations. The Hamiltonian is a generalization of the Hamiltonian that I had described for the classical dimer model. There's a potential energy term where the potential energy vortex essentially gives some strength V whenever there are two parallel dimers in a plaquette. And in the quantum model, we also add a kinetic energy term, which essentially flips the plaquette by 90 degrees whenever there is a flippable plaquette. In other words, whenever there are two parallel dimers in a dimer configuration. So the matrix elements of the kinetic energy term are these, and the matrix elements of the potential energy term are these. And the full Hamiltonian of the quantum dimer model can be written this way. Now, the question that we set out to answer is what is the phase diagram of the quantum dimer model as a function of the temperature and the interaction potential if we treat T to be 1, the kinetic energy coefficient coefficient of the kinetic energy term to be 1. So yeah, hope the axis is clear. So if V is equal to 1, the system is gapless, and in units of T, if V is equal to 1, the system is gapless. The ground state is known, and it's well, at that point, the ground state is a uniform linear combination of all dimer configurations, and that point is called Rokhsar-Kivelson point. So that will be this point in our phase diagram. Now, if temperature is infinity, then the terms in the Hamiltonian do not matter. The configurations are simply the uniform. The partition function is essentially a uniform infinite temperature ensemble of all possible dimer configurations. So this should essentially be equivalent to the classical 2D dimer configuration, non-interacting 2D dimer configurations, and therefore, in that limit, we should be able to say that it is described by a Coulomb gas with G given by half, which we know from mapping to free fermions. In the extreme negative minus infinity value for V, we know that the kinetic energy term is inconsequential, and if you tune temperature, there will be a critical value of temperature below which the negative value of V will favor parallel dimer configurations. Those parallel dimer configurations, tendency to form parallel dimer configurations, would force the system to order into a columnar phase. So that happens at a value of temperature, which is Tc by V, which is known to be 0.65. At higher temperature, it is described by a disordered Coulomb gas. In the other limit, when V is large but positive, again, the kinetic energy term is inconsequential, and I have a classical Hamiltonian for the dimer model, and in the classical dimer configuration, it is known that at high temperature, there is a disordered Coulomb gas, and at low temperature, there is a staggered phase. Picture of the staggered phase. Oh. Okay, I don't have it. A staggered phase consists of dimer configurations where there are no parallel dimers. This can be constructed by having dimers sort of staggered relative to each other in two adjacent lines of the square lattice. Now, the simplest phase diagram that you can guess from this is something where there is an ordered columnar ordered phase all the way till the RK point. We know that just above the RK point, it is believed that just above the RK point, the system is, and the RK point is gapless, and therefore, a simplest phase diagram that you can guess looks like this. You have something like a columnar order all the way to RK point, something like a staggered phase all the way till on the right side of the RK point, and a gapless phase up above. Now, the gapless phase can be further classified based on the effective value of G, and what we managed to describe, what we managed to do using our algorithm is to map out the values of G in this critical phase. And
can we go back a step? So you're plotting the phase diagram there, and you explained, the classical phases, and so basically you would plot this phase diagram in terms of some could be an order parameter, or could be the free energy or something.
Right.
And then just before you switch slides, you put G.
Right.
So the effective G you would get in the Saint-Gordon theory.
Right.
So is there an obvious connection between those two?
So at the infinite temperature, we know that
No, that's clear.
Yeah.
Yeah, but then you're saying, oh, it looked like you're going to map out the phase diagram as G as a function of B and T.
Mm-hmm.
While I was expecting you were going to show the phase diagram in terms of an order parameter or the free energy.
The obvious ordering that can appear in that region are the columnar order or the staggered ordering, and all those order parameters are 0.
Okay.
We get a liquid of dimer configuration. Have a liquid phase.
Yeah, but in terms of these phases, it's properties of the height field, for example.
Right.
You know,
We're calculating the
properties of the height field at T and B.
We are calculating the gradient of the variance of the gradient of the height field, and that can be used to infer G.
Okay.
G would be the stiffness.
The stiffness. Okay, yeah, G is the stiffness of the height.
Yeah. So what
Okay.
we will do is use the. Yeah, I didn't describe that. I have it in a later slide. You can show that you can define a flux for the from the dimer configurations, and that flux turns out to be the gradient of the height field.
Sure.
And we look at the stiffness of that flux, and that turns out to be the expectation value of the square of grad H.
And then the other question before you show us the actual results. So should I expect something to happen at B equal to 1 at all temperatures? And the reason I ask is that the partition sum is exponential of the Hamiltonian. The Hamiltonian is a stochastic operator at B equal to 1. That's a Rokhsar-Kivelson point. So this is really the partition sum of classical trajectories. If you do quantum partition sum, is the trace. So it's counting classical stochastic trajectories that return to the same initial point.
With
the time boundary conditions, the partition sum would be 1. For other boundary conditions, it's the free energy 0 along all that line. For this exactly that same reason. So the question is whether there will be something special along that line.
We did not see anything special along this line. Indeed, when we that is one of the last slides, but indeed when we don't see any ordering here. When we calculate G as a function of parameters, we find that there is a constant G line that actually curves around. We don't see anything that is systematic along the vertical V equal to 1 line. Within the order parameters and the quantities that we looked at, there is nothing special. So then the question is how can we sample? How can we understand the partition function, or how can we calculate expectation values of quantities in a constrained model like this? Similar problem has been studied in spin systems, where you can calculate the expectation value of finite temperature expectation value of various quantities, and the simplest algorithm that can be used there is the simplest quantity that can be since the simplest algorithm that can be used is the stochastic series expansion. The idea of stochastic series expansion is essentially, to put it in one line, it's essentially sampling over all possible Feynman diagrams that are described by this Hamiltonian. More precisely, I can describe the expectation value of an operator as the trace of e to the power minus beta h, and I can expand e to the power minus beta h as a sum over the trace part can be expanded as a sum over basis state, and the basis can be taken to be the computational basis, which is the set of all classical dimer configuration, and then there is a sum over n, which essentially is comes from the expansion of the exponential, and I have a expansion of this kind. Now, if I look at h to the power of n, for simplicity, let's ignore the minus and beta to the power of n, etc. Then, if I have some quantity that looks like a plus b, the whole expectation value of a plus b the whole square, I can write it like this, and it is essentially the sum of all words of length 2 made of alphabets a and b. Why 2? Because I had an exponent 2. Why a and b? Because in the quantity that I raised to the power 2 contained 2 entries a and b. So if I, if I look at the quantity h to the power of n, it will be the sum of all, it can be thought of as the sum of all words of length n made of the alphabets that are contained in H. And what are the alphabets that are contained in H? They are the interaction vortices that arise from these two terms. It could be the kinetic energy terms Ti on each placket, or the word potential energy terms VI on each placket. All right. Now, sorry. Okay. Yeah. Now, if I consider it that way, then I have a sum over three variables. One is the classical configuration psi, a sum over the lengths of the words, and then sum over all possible words of that many lengths made up of these alphabets Ti and Vi. Now, if we assume that there is a upper limit at low temperatures, we'd expect that beta is very large, and this quantity increases with n, but the expectation value decreases with n, and n factorial also 1 over n factorial also decreases with n. Moreover, for large values of n, the value of this term is 0 or decreases. So there is a typical, there is an upper limit on the value of n that appears in the expectation value. And therefore, I can think of this as, I can put an upper limit on the largest size of word n in the summation. If I do that, if I treat the upper limit to be m, then I can do a little bit of combinatorics, and with those, the summation can be rewritten in this form. I have assumed that the operator whose expectation value I'm calculating is a diagonal operator in the computational basis. In that case, O acting on psi is just a number O psi. And the summation reduces to this. It's a sum over all classical configurations, sum over all words of length m, and LW is the words essentially are made up of our operator sequences made up of kinetic energy term Ki, potential energy Vi, or identities, and LW is the length of non-identity operators in the word W. Okay, so which I'll call the length of the operator sequence. Okay, so why do I have identity operators included? I said that I'm putting an upper limit on the largest word length m, but I could have terms where the number of the exponent n is less than m, and I think of those configurations to be certain operator sequences padded with identity operators. Okay, so I'll explain this. It's a little hard to explain this with the dimer configuration because there were 2 + 1 dimensions. So I'll explain this with 1 + 1D XXZ chain, I think the original algorithm by Sandvik was described in this model. I might be wrong, but the stochastic series expansion in the XXZ chain can be written this way. That, by the way, the XXZ chain has a ZZ interaction and an XY and an interaction in the XY plane, whose coefficient I'm calling V. The interaction in the XY plane can be written as an S plus S minus S plus term, which essentially raises and lowers adjacent sites spin values. By the way, I'm thinking of spin half particle, so spin half system, spin half chain. I have S plus S minus terms on adjacent sites such that the total SZ value is conserved. I can think of this as a sum of a diagonal operator SZ and the non-diagonal operator Nij, which is given by this. Okay, so the Nij essentially is a swap operator. In this case, I can again use this expansion, which is same as what I wrote earlier. And then I can think of the expectation value of an operator O to be the weighted average of O psi with a probability distribution that is given by this quantity. So I just need to construct a Monte Carlo, design a Monte Carlo that will create a set of samples of configurations psi and words W with this probability distribution, average of psi over this probability distribution will get me the expectation value of psi in the thermal ensemble. And I can think of this term, the value of the probability distribution for a given psi and given word length to be a Feynman diagram of this type. Why do I call it a Feynman diagram? It is essentially some initial state which is equal to the final state, and there is a sequence of operators that scatter from one time step to another. These green lines and red lines are the diagonal SZ operator. The green lines are the diagonal SZ operators, and the red lines are the swap operators. And I consider all possible Feynman diagrams which scatter this initial state back to initial state, passing through various sequence of transitions. And by the way, these operators can be located at various different points, and therefore there are various possible sequences in which these operators can act. Okay, so the value of this operator sequence and this state psi is the value of this Feynman diagram, which is given by this. Okay. Now we just need to sample the configurations with, I just need to find some Monte Carlo rule, which essentially implements this probability distribution, and that will get me the right sample. So in order to get this transition, I need two kinds of moves. One is something that can insert a diagonal operator into a place where there are no operators. By no operators, I mean there is an identity operator in this time slice. And I need to insert, every time I insert such an operator, the value of this Feynman diagram changes, and therefore I need to insert the operator at some previously unoccupied time slice with a probability, with a rate that satisfies the desired detailed balance condition. That essentially samples configurations with the same locations of the non-diagonal operators. Now I need a second algorithm which allows you to make a transition from diagonal operators to non-diagonal operators. And this is done using a worm algorithm, which essentially, which essentially starts by arbitrarily finding a diagonal operator, changing the direction of the spin, and every time, and if you take a time slice and change the direction of the spin on that time slice, then there is a discontinuity in the spin configuration in one of the time slice, across one of the time slice. So I can think of sending an update instruction across that time slice that keeps moving in the forward time direction. And if there are no operators in some time slice, I can just move the update instruction forward. But the moment it encounters a vertex, it has to do something else. It can, for instance, if it encounters a diagonal vertex, it can modify it can continue forward without modifying the configurations, in which case the only way in which only possibility is that there is a diagonal vertex here, or this update instruction can swap to the adjacent side, but in that process change the vertex from a diagonal vertex to a non-diagonal vertex. And you can think of the reverse process, and in order to implement the reverse process, you need to have reject certain dimer updates, but those are details. But this move essentially allows you to change diagonal vertices to non-diagonal vertices. And the previous step here allows you to change from identity vertices to diagonal vertices. And with these two, you, at least in principle, should be able to get, we believe that you get an ergodic sampling of all possible words of operators and configurations. Why do I say that I can also sample configuration? Because as this worm moves forward, the spin direction also flip, and therefore the spin configurations also change. And these moves allow you to change from diagonal operators to non-diagonal operators. And this update instruction is moved forward, and when it reaches the upper end, it just continues from the lower end, ensuring that periodic boundary condition is satisfied in the imaginary time direction. And we wait until this update instruction comes back to the initial point, in which case all the discontinuities in the adjacent time slices are gone. Okay, so then you get a valid configuration again. That's roughly the idea of the stochastic series update. Now, the question is, can we do this in the dimer configuration? So the idea is the same. I need to sample psi and the words in such a way that the detail balance ensures this probability distribution for the configuration psi, dimer configuration psi, and the operator words W. Here I have two kinds of vertices. One is the diagonal vertex, which takes some configuration without, which can occur between two time slices where the dimer configurations are identical. Or you could have a non-diagonal operator between two time slices where one of the plaquettes has a pair of dimers that has rotated by a 90-degree.
Sorry.
Yeah.
I think you explained it and I missed it. If you go back another slide,
yeah,
you have the expression of the. You're trying to sample this probability capital P.
Yes.
And you have this scheme where you change, what you call the graph that corresponds to that. Now, if you do it at a Monte Carlo, what you need to know is you need to know the ratio of these P's.
Yeah.
What I'm a bit confused is that this P is not first of all, the partitions are there. The normalization is missing, but that goes in the ratio. But this is not explicit because you have psi W psi, yeah, and then you would have psi W prime, your proposal. So if you want to make a Monte Carlo, you need P of W and P of W prime. I'm assuming that the psi's for the moment are the same. How do you calculate that ratio, given that you do it explicitly, you calculate the matrix element for every move?
Yeah.
So you have your W, you do the matrix element, you propose another W, you calculate a new matrix element, and you use the ratio to accept or reject.
Yeah. So the probability distribution is not simply on W. It is a joint probability distribution.
But if you change from one W to another W.
I'm also, when I change from one W to another W, the matrix element changes. Psi might change.
Okay. And you compute it explicitly.
Implicitly, I do compute it.
Okay.
Basically, instead of computing the change between the initial and final choices of psi and W, at each step, I change W or psi in such a way that.
You can do it accumulatively and
exactly.
It's more efficient.
Yes.
I see. Okay.
It's more efficient to do it. Okay, so in the in the quantum dimer case, idea is essentially the same. I have diagonal operators which do not change the dimer configurations across two time slices, or non-diagonal operators which flip the dimer configuration in one of the flippable plaquette. Okay.
Sorry, can I ask something? The algorithm you have has no dimer conservation, but whatever you show here for the models have dimer conservation.
Okay, that's my next point. Thanks.
Okay.
So what makes it difficult, what makes it easy in the spin case is that I can locally flip the spin and nothing, nothing bad happens, the probability weight might decrease, but it is still an allowed configuration. In the dimer case, it is harder. We need to satisfy a hard constraint. Or in other words, if you randomly flip a dimer constraints are violated, and essentially the probability distribution is 0. So you have that kind of a move is extremely inefficient. You will just go to dimer configurations which are not allowed at all. Yeah. Okay, so that is what makes the same problem in the dimer case harder. Sorry for the change in color. That's because when I gave the talk in some places, some of the slides were not visible at all, and then I made 2 versions of it, and somehow both of them are in this slide. Okay. Okay, so one part of the algorithm is the same. By the way, this algorithm, this first part of the algorithm that I'm mentioning was originally proposed by Silverson and his collaborators in 2019, and they called it the sweeping cluster algorithm. Not sure why. Okay, so the first part of the algorithm is similar to the spin case. What is that? That essentially amounts to taking a time slice which is separated by an identity operator and inserting a diagonal operator between them. That doesn't involve changing any of the dimer configuration, and therefore there is no, you don't need to be very careful. You just randomly pick a placket and see if, and you can insert a diagonal operator there. The weight, the probability weight changes, and therefore you do this process at a rate that satisfies detail balance. Now, the second part is of inserting a non-diagonal operator is the difficult one. Okay, so what you do is this. I identify a placket which has a diagonal operator. Sorry, the flippable. I identify a flippable placket in a configuration, and then I rotate that by 90 degrees. So where did I? Yeah. So I took this placket and I rotated it by. I already rotated it by 90 degrees. And when I rotated it by 90 degrees, there is a discontinuity. There are 4 discontinuities between that time slice and the next time slice. So I send upwards 4 update instructions, basically saying that the configuration above has to be flipped. If there are no operators just above it, it's simple. I just flip the configuration of the timers just above it. But if there was an operator here, then yeah, if there was an operator here, then I change the operator as well as change the number of update instruction above in such a way that the detail balance is still satisfied. Okay, let me see if I have a slide for this. Okay, so yeah, so if I have 4 update instructions coming from having rotated the dimer configuration here, in the next time step, I could change the operator configuration, the vertex configuration, and also increase or decrease the number of update instructions above, or just continue without changing the vertex. So the bottom line is that I keep the generalization from the spin case is that as I keep updating the vertices in the successive configuration, I allow the number of update instructions to proliferate. In the spin case, I had only 1 update instruction in every successive time step. In the dimer case, I have a proliferating set of update instructions. And when I say proliferating, it may turn out that at certain vertices, the number of update instructions might decrease. So the number of update instructions keep increasing or decreasing depending on which vertices it crosses. And we keep doing this until the number of update instructions comes back to 0.
Okay. Oh, sorry. That doesn't sound so straightforward. This is like a bridge problem.
Yeah.
Like in stochastics, right? So,
Yeah.
so you control where you start, you don't control where you end.
Right.
So in your case, these arrows are growing.
Growing.
You need them to come back
Could,
because
yeah.
you have the trace.
Yeah.
Or you have the psi side.
Yeah.
How do you make them come back?
We just follow the rules, and it turns out that about 10% or so of the loops just don't end even after our patience ends. So we just abandon those moves.
Okay, but a large fraction comes back.
Surprisingly, a large fraction comes back.
Because usually it's at least polynomial.
Yeah, you would have expected that it won't come back.
Yeah, you can go around.
Yeah, you keep going around.
Lines.
Yeah.
With your bridge, you have to, you start here and you have to get back to here. But in this case, you can go up and then
Until
keep going around.
so you improve your chance of coming back because you keep going round and round and round.
We don't improve the chance of coming back because the number of update instruction can just proliferate. Here, I start with 4, it might go to almost L.
In a bridge problem, the number of bridges decreases either polynomially or exponentially with time. Because trajectories are expanding and fewer and fewer in relative terms come back.
Yeah.
It sounds like here is not a it's not a major issue.
We just know this empirically that only about 10% becomes uncontrolled.
Okay, that's very good.
Yeah. So that otherwise this whole algorithm would fail.
Isn't it more like a random walk where you just wait until it comes back? You're not.
Well, exactly. Random walk is polynomial. A bridge is polynomial in time, the fraction. This is 1 over some power of the number of steps. So I'm not saying it doesn't come back, but
But it sounds a lot easier than the bridge, like you can fix that once. Because you can wait as long as you want until it comes back.
it's not a fixed time.
Oh yeah, it's not fixed time. I just keep
Well, the term probability is still polynomial time.
Yeah.
Okay.
because the system size is finite. The spatial extent is finite, so that probably puts the constraint on this.
It could be better.
Okay. So
If your walk took a very long time to come back, then
I
that's
just
great,
abandon.
because you've done a lot of updates.
Yeah.
Oh, you gain in
autocorrelation time.
you decorrelate your Monte Carlo.
Yeah.
Yeah, but that also depends on the ratio between
Right.
probabilities.
So in practice, what we did is we put a cutoff on when we lose patience, and then
It works, it's nice.
okay. Now the problem with this is that typically the update lines are confined in a compact region. It goes up, it goes about, moves around in a finite spatial extent, but it goes around in time many times in the periodic direction, but in the spatial extent, it's confined. If you locally change dimer configurations in a small compact region within the 2D plane, it turns out that kind of a move is not ergodic. How do we know that it's not ergodic? You can define a quantity called winding number, which is essentially the flux stiffness. It is the value of the flux or the gradient of the height field. In terms of the dimer configuration, you can think of it this way. You can think of dimer constraint as a divergence-free condition by saying that whenever there is a dimer connecting a sublattice to B sublattice of this bipartite lattice, there is a flux of 3 going from A sublattice to B sublattice, and whenever there is a line from A sublattice to B sublattice where there is no dimer occupied, there is a flux of -1 going between them. With that, you get a set of fluxes that go from one node to other, and the condition that there is only one dimer, there is exactly one dimer connected to each plaquette, so each node or vertex, is equivalent to the condition that there is no net the divergence of this flux is this field is 0. Now that means that I have a quantity whose I have a flux which is conserved across different layers. The flux would be the integral of this field across one axis or one surface. The surface in this case would be a line that cuts through the dimer configure, the 2D plane. The value of the total flux of this field across one line is going to be independent of where I draw that line. For instance, if I calculate that flux here, it turns out to be 0. If I calculate that flux here, it again turns out to be 0. And you see that this dimer configuration is related to this dimer configuration by some local move that I made in this small region. And it turns out that if you make any local move inside a dimer configuration, the value of this flux will remain unchanged. On the other hand, if you make a non-local move, for instance, if I take a line of dimers and completely move it forward by 1 unit, then I'm changing L dimer locations. In that case, the flux changes by 1 unit. I haven't given the details, but the idea is that if I don't do non-local moves of the dimers, the flux value will not change. Now, in the update rules, update scheme that I mentioned earlier, the one that was given in Silva's in his paper, that does not allow non-local dimer moves, and therefore the flux is not the flux value is not ergodic. Okay, so having we could improve that algorithm by appending this part to the original algorithm. What we do is take a particular time slice and perform what is called a directed loop update. Now, to do a directed loop update, there is an efficient algorithm that allows you to sample 2D classical dimer configuration, which is ergodic. What we do is in each time slice, I perform a directed that I basically use that algorithm to sample configurations. However, these updates should be consistent across time slices, given that there are vertices between them. If there are only diagonal plaquettes, then there are no constraints that I need to satisfy. There is a configuration where all the I can just update every layer in the same way. It gives me a valid configuration. But if there are non-diagonal plaquettes, then that gives a very complex constraint across different time slices. So to resolve that, what we did is just freeze the dimers around around any non-diagonal plaquette. So in here, I have non-diagonal plaquettes marked as green and diagonal plaquettes marked as blue. Wherever I see non-diagonal plaquettes in any of the time slice, I freeze the dimer configuration there. And I allow a directed loop update anywhere else. Now, I also need to satisfy some detailed balance conditions regarding the location of the non-diagonal plaquettes, sorry, the diagonal plaquettes. What I do is I say that whenever a non-diagonal plaquette is affected, I associate an effective interaction between dimers in that plaquette, and that effective interaction can be calculated. So the equal time update can be described as follows. I take any location in the full space-time configuration and freeze any configuration where any plaquette where there is any non-diagonal vertex. And wherever there are diagonal vertices, I associate an effective interaction between the dimers in that plaquette, and then perform a directed loop algorithm, which can sample this 2D configuration. And in that case, it turns out that we can successfully sample winding number sectors and calculate monomer correlations or whatever that we want to calculate. And this, at least in the winding number sector, it is ergodic. If there are too many non-diagonal plaquettes, we will have to freeze a large number of plaquettes, and that makes very little room, that leaves very little room for the directed loop update to be performed. And in those cases, then the algorithm fails. And it turns out that at high temperatures, this is not an issue. At very low temperatures, the size of the size of the system in the time direction diverges, and therefore the probability that there is a non-diagonal plaquette on any of the non-diagonal vertex on any of the plaquette increases, and it essentially freezes the entire dimer configuration and the update phase. So with this, we can calculate the map of the system. We find that there is a columnar order parameter below some temperature on the negative value on values of V, which are lower than the RK point, to the left of the RK point. On the right side of the RK point, for V greater than 1, we get a staggered phase. We can calculate G, the effective, the flux stiffness, as the expectation value of the winding numbers, sorry, the expectation value, the variance of the winding number. And as I go from, or 1 over the variance of the winding number. Basically, from the winding number, I can estimate the flux stiffness and map out the constant G lines for the negative V side. As I lower the temperature, the effective flux stiffness increases, and at some point it reaches a value where the KT transition condition is satisfied, and it crosses over to the four-pole symmetry broken columnar ordered phase. On the other side, where V is larger than 1, the winding number keeps increasing, and it reaches a maximal value when it transitions over to the staggered phase. The algorithm is not reliable at very low temperatures, and in particular, the region around the RK point is not very reliably mapped out. The constant G lines look like this. The G equal to 0.5 line essentially goes like this. The question you had asked was whether something special happens at V equal to 1. We couldn't see anything, at least with the quantity that we had looked at. Okay, and this is the quantity. We can invert this relation to calculate G from the winding number, variance of the winding. Okay, we checked what the finite size effects were, and at least for the parameter regimes that we looked at, the finite size effects were minimal. Okay. All right, so okay, those are details of how the critical points were determined. And we can also do a high temperature expansion, which details are there in the paper that mentioned. And the high temperature expansion essentially reproduces the constant G lines that we could get from Monte Carlo calculations. Okay, so I'll leave with this. Hopefully, I was able to give the flavor of the algorithm. Essentially, it can sample the constrained dimer configuration, even though there are strong constraints that prevent the standard stochastic series expansion to fail. Okay, so that's the summary.